Hi guys, Audrey here. Let's calculate a determinant. So here we have calculate A equals to this matrix. Notice that the matrix has straight lines around it, not the brackets, but the actual straight lines. Those straight lines tell us that we're calculating the determinant. So we don't need to specifically say calculate the determinant. The straight lines tell us that. Okay, so this is a 3 by 3 matrix. So there are multiple different ways that I could go about it. We're going to pick two of them. The first is we're going to do this entirely using cofactor expansion. And the second is we're going to use the 3 by 3 trick. So first, when we're doing cofactor expansion, that's where we will start, cofactor expansion, we need to pick a row or a column. And we know that picking a row or a column with zeros is a good plan, because we're going to have to calculate the cofactors for every non-zero number in that row or column. So in this case, I can see that the second row or the third column has a 0. So I'm going to go ahead and go with the second row. Either the second row or the third column would be good. So cofactor expansion across the second row. So what this means is my determinant of A will equal to 1 times the cofactor in the second row and the first column, plus 3 times the cofactor in the second row and the second column, plus 0 times the cofactor in the second row and the third column. So you see, I'm multiplying that third cofactor by 0. So I don't actually have to calculate that cofactor. That's why it's so important to pick the row or the column that has the most zeros, because it just eliminates so much the number of cofactors that we're having to calculate. Now I'm just going to do my little plus minus matrix here. We're just alternating the pluses and minuses. And we're going across the second row. So that means I'm going to have a minus, a plus, and a minus. So here, this is going to be minus 1 times what happens when I get rid of the second row and the first column. Second row gone, first column gone. What I have left is negative 2, 6, 5, 4. Then we're in a plus place. So this is plus 3 times what happens now when instead of getting rid of the first column, I get rid of the second column. So I'm going to move that line right there. And we have negative 2, 6, 9, 4. So by doing cofactor expansion, we've reduced this. So now instead of having one 3 by 3, I've got two 2 by 2 cofactors to calculate. So we know how to do 2 by 2. We just multiply the diagonals and then subtract. So this is equal to negative 1 times negative 2 times 4 minus 5 times 6 plus 3 times negative 2 times 4 minus 9 times 6, which gives me negative 1 times negative 8 minus 30 plus 3 times negative 8 minus 54. Which is negative 1 times negative 38 plus 3 times negative 62. Okay, so we just add these together to get 38 minus 186, which gives us negative 148. So the determinant of this matrix is negative 148. And we did that entirely using cofactor expansion. Now, why is this answer useful? Well, for lots of different reasons, but for us right now, the main thing is that the negative 148 does not equal to 0. So that actually tells me a lot of things. That tells me that A is invertible. And A being invertible means A reduces to I. A has a pivot in every column. Any system of equations for which A is the coefficient matrix will have just one solution, a unique solution. So we actually have lots of information just from knowing that the determinant is not 0. Okay, let's do this using our 3 by 3 trick. So we're calculating the same determinant. We should still get the same negative 148 that we got up there. We're just going to use a little bit of a different method, the 3x3 trick. And what this trick tells me to start off doing is to take those first two columns and rewrite them at the end. So the 3x3 trick is a lot like taking the determinant of a 2x2 matrix, doing the diagonal minus the diagonal, but with more diagonals. So first, we're going to do our positive diagonals. So I'm going from left to right, top to bottom, and I'm going to multiply all of these numbers together. So this determinant will be equal to negative 2 times 3 times 4 plus negative 2 times 0 times 9 plus 6 times 1 times 5. So I do all of my diagonals starting in the matrix, left to right, top to bottom. 6 times 1 times 5. And then I subtract, same as when I'm doing the 2x2, I subtract the other diagonals, the diagonals going from right to left, top to bottom. So now I'm going to start at the right side. This diagonal gives me negative 2 times 1 times 4, negative 2 times 1 times 4, plus negative 2 times 0 times 5, plus, oops, my last diagonal here, 6 times 3 times 9. All right, so then we just have to calculate these numbers and we should get negative 148 again. So this is equal to negative 4, 12, 24, so that's negative 24 plus 0, yay, plus 30, minus negative 8 plus 0, again, yay, 6 times 3, that's 18 times 9, that is 90 plus 27, that is 117 plus 117. There we go. And this gives us 6 plus 8 minus 117. And by 117, I mean 6 times 3 times 9, 162. So this is plus 162. So that's minus 162, and this does indeed give us negative 148. So we ended up with the same value. So the determinant of A, is equal to negative 148, and we got the same answer in 2 different ways. That's all. Bye, guys.